Welcome my friends, welcome to my next lecture. Now in my last lecture I was talking about branch of a multivalued functions. In fact I started with elementary functions like exponentials, then trigonometric functions, then I have defined what is called log functions. Then while discussing with log functions, then branch cut, branch point I have discussed. Okay, so multivalued functions and concept of branches. So now for today's lecture my plan is to talk about, to move our discussions to what is called Riemann-Stieltjes integral. In other words, I am going to define what is called contour integrations. For contour integrations, you need to know a very little bit about Riemann-Stieltjes integrations. Then we have a contour integral, then path independency, and then we will have one of the most fundamental theorem in complex analysis, that is called Cauchy-Goussat theorem. So my plan is to talk about starting with the discussion of Riemann-Stieltjes integral and then try to develop the theory a little bit so that I can talk about what is called contour integrations. Okay, so as I said, so today I'll start with the discussions of integrations. Okay, so first I'll talk about the meaning of integrations of a nice functions f given, say let it be complex valued functions, say suppose domain is contained in real number, and then I'll talk about what is called the contour integrations. Contour integration means what? That means if I have a complex valued functions on some domain subset of the complex plane, and if I take some, say some contour, I'll talk about what do I mean by contour, and if I take a contour in my domain, then what is the meaning of integrations over that contour of your functions f. So but before that, let me start with very simple case of integrations. This time I am talking about the integrations of complex valued functions, but your functions domain is sitting inside R. Now if I just talk about, like, if you are recall your definitions like Riemann integrations, say if I have a functions from closed interval AB to R, suppose this function is continuous functions, right? Then you know the meaning of Riemann integrations a to b fx dx, right? So what is that? If I just quickly recall, that means you have to have the interval a to b, correct? Then you have to take a partitions of your interval ab, let it be p, which is nothing but a set of points x0 is equal to a less than x1 up to xn minus 1 less than xn is equal to b, right? If I take a partitions, then what you have to do, there are many ways you can do that. Either you can say that, okay, I will define upper sum, I will define lower sum corresponding to the partitions. Then I will say that a functions f is Riemann integrable if upper sum is exactly equal to lower sum. Another way this is equivalent with the definition is that given a partitions of the interval a to b, then you form a Riemann sum. And if the partition goes to finer and finer, that means if partition's norm of the partition goes to 0, then you can say that my function is Riemann integrable, and limit of this Riemann sum is the value of the integrations. So that is the best way. So that means if I say that this is my Riemann sum corresponding to the partitions, which is nothing but sum over I up to 1 up to n, then what you have to do, then f at the point xi I, then length of the interval partitions xi to xi minus 1. Okay, and what is xi? Xi is some point in the interval xi minus 1 to xi, any point, right? Any point in the interval xi minus 1 to xi. Then I want to make sense integrations of f with respect to dx Riemann integrations. That means what you have to do, you take any point xi in the interval, make the sum I from 1 up to n, that n depends on the partitions, number of partitions points, then length of the interval, and then what you have to do, that limit norm of p approaches to 0 of this object. Then what is the meaning of norm of p? Norm of p is nothing but, you can say that this is the maximum of the length of the interval, that means xi minus 1, 1 less or equal to I less or equal to n. Okay? So this is the norm of the partition. So that means if I take the norm of the partition goes to 0, that means I am putting more and more number of points in the partitions. That means length of the interval of the partition goes to very small. If this is the case, then one can check that if my function is nice, say let it be my function is continuous functions, then if limit norm of p approaches to 0, this Riemann sum, this limit exists, and it will give you some value, let it be some number I, and which I denote it as integrations a to b fx dx. So that kind of definitions you know in the real case, that means real valued functions defined on the closed interval ab, and your function is continuous. Now what is the difference between that notions and the notions I am talking about here? So this time what I am doing, I am just taking complex valued functions, but domain I am keeping in the real line. Okay, that means closed interval a to b. Now you will see the same definitions I can capture here itself. So only the fact is different is that this time my functions is taking value in complex numbers. But later on, but I already talked to you that already discussed, like any functions f, say taking complex valued, say from A to B, then you'll see I can break my functions into two parts, right? So one is u, another is v, and both u and v are functions from R to R. And R to R integrations you know. So therefore you have to just define integrations of f. Okay, so that's what it's exactly going on. Look, so first I would like to give a sense of integrations of my complex valued functions defined on closed interval a to b. Look, so let closed interval a to b to c be a complex valued functions of real variable t. Now once I have that, since my functions taking complex valued, so therefore I can break my functions into two parts. One is ft is equal to ut plus ivt. What is u and v? U and v is very nice. U is a functions from closed interval ab to r. V is a functions from closed interval ab to r. Okay. So therefore I can break my functions into two real valued functions from the interval a to b. And then now I am defining it, I am giving the definitions. The definitions integral of a complex valued functions f over the interval ab. This is my notations, integrations a to b ft dt, which is nothing but integrations a to b ut dt plus I times integrations a to b vt dt. That is the kind of, that should be the natural, right? But these notions you know from your real analysis. So this, suppose this limit exists, then you can say that my functions is integrable and the value is nothing but this plus this. So when the individual integrals in the right hand side exist. So therefore now definition is very clear. So if I consider a complex valued functions from the interval a to b, first what you have to do, you just write your f into two parts like ut plus ivt, where u and v are functions from closed interval a to b r. You know the meaning of integrations a to b ut dt, integrations a to b vt dt from the knowledge of your real analysis. Then you can say that, well, I'm saying that my functions is integrable and I'm defining it integrations a to b ft dt, which is nothing but integrations a to b u plus I times integrations a to b b, provided that both the integrals should exist. So if I have these definitions, one thing is kind of quite clear. So the left hand side, it will be a complex number whose real part is this and imaginary part of this. So that's what the real part of the left hand side, which is nothing but a to b ut dt. But what is u? U is nothing but, look, f is ut plus vt, right? So u is nothing but real part of f. Okay, so therefore real part of the integrations is nothing but a to b real part of ft dt. That means in some shape you can say that real part of the integral, I can push the real part inside the integrand. That's what you can think about. So real part of these integrations is nothing but integrations of the real part. That means I can push my real part inside the integrand. Similarly, you have this one, imaginary part of a to b ft dt, which is nothing but a to b imaginary part of ft dt, because vt is nothing but imaginary part of f. So therefore I can push real and imaginary of my integrations inside the integrand. That's why you can think about that. In fact, it follows from the definitions of the integrations the way I have given. So therefore integrations of complex valued functions from the closed interval a to b is well defined, right? So as long as my integrations u and integrations v exist, then I am done. So one of the sufficient condition, you can say that if I start with a continuous functions f from closed interval ab to c, then one can easily prove that the continuity of f implies the continuity of u and v. And once I have a continuity of u and v, then the corresponding Riemann integrations from the knowledge of real analysis, you know integrations a to b u exist, integrations a to b v exist, and therefore integrations a to b f exist, and which is nothing but this is the corresponding value. So that's what I have written. Look, so if my functions f, which is ut plus ivt, suppose it is a continuous function, then it is exists, because if f is continuous, so it's f is continuous implies u and v are also continuous. That one can prove it. Okay, and u and v are continuous functions means integrations a to b u dx, right? I think what I have written dt. So u dt plus and integrations a to b v dt exist. This will implies integrations a to b f exist. Correct? So one example I have talked about. So suppose your ft is like e to the power t plus I times t square. Okay. So then what is the value of the integrations? So therefore you can then from the definition you can easily calculate. So now if I have f is equal to u plus iv, there is a theorem you can, if you remember, f is continuous, or you can think about f is equal to u plus iv, or it is of the form you can say that f u comma v. It's up to you. Then one can prove that f is continuous on a to b if and only if u and v are continuous on a to b, right? So that's theorem you can prove it. By just using the definitions of continuity of a complex valued functions, you can say that f is continuous. I already discussed when I was talking about existence of limit and continuity. F is continuous means component functions, that means u and v are component or real part, imaginary part, these are continuous functions, and if the real and imaginary or component functions are continuous functions, my whole function f is continuous. Now look at these functions f. What is my u? My u here is actually u of t is equal to e to the power t, and what is my v? V is nothing but t square. Now both u and t are nice functions, exponential function, polynomial functions, right? So these are continuous functions. So therefore f is continuous functions. So therefore this left hand side limit exists. And what is that by definitions? This is nothing but integration 0 to 1 ut dt plus I times integration 0 to 1 vt dt. And you just easily calculate it. And if you calculate it, this is the corresponding integrations. Okay? So therefore I have not done anything extra. Whatever knowledge or whatever kind of concepts you are familiar with in case of real analysis, I am just adding just this plus I times this, that's it. Okay. So now you can talk about what is called antiderivative of primitive. What is the antiderivative of primitive? Like if I have a function f, if I say that there exists a function capital F such that whose derivative is my small given functions f, then I can say that this capital F is nothing but the primitive of f. And if I have a primitive of f, then I can easily calculate my integrations a to b f ft dt by using fundamental theorem, okay, using the primitive. So that is why I can say that this I am just giving some information. So let f is equal to ut plus I vt where t runs from closed interval a to b. Suppose that there exist two functions capital U and capital V from closed interval a b to r such that capital U prime t is equal to small ut, capital V prime of t is equal to small vt. That means I can say that U and capital V are the primitive of small u and small v respectively. Then what I am doing is that I am considering a capital F functions which is capital ut plus I capital Vt. Then by the definitions of derivative, if I calculate the derivative, since capital U and capital V is differentiable, so therefore capital F is differentiable, one can prove that. And capital F prime of t, which is nothing but u prime of t plus I v prime of t. But what is u prime of t and v prime of t? This is nothing but ut plus I vt. And what is that ut plus I vt? It is nothing but f of t. So therefore satisfies these equations, and it is called the antiderivative or primitive of f. So antiderivative or primitive of small f means I should have the existence of one functions, let it be capital F, from closed interval a b to c, such that if I take the derivative of capital F, it should exactly equal to my small f. So what I have said is that, so if I have a expression f which is of the form ut plus I times small vt, and if the primitive of small u and small v exists, so let it be capital U and capital V, then we will have the existence of primitive of small f. So what you have to do, you just write capital F which is capital ut plus I vt, which is differentiable because capital U and capital V are differentiable functions, component are differentiable, and therefore it will imply that capital F prime t which is exactly equal to small f t. So then by fundamental theorem of calculus, in the real case, so what is the definition? Integration a to b f t dt. By definition, this is nothing but a to b ut dt plus I times integration a to b vt dt. That means this is the one, right? But what is integration a to b ut dt? So a to b ut dt, which is same as a to b, but u small u has a primitive, that means exists, so capital U prime of t dt, right? And then by fundamental theorem, what is the value? ub minus ua. Similarly, you can say that integration a to b vt dt, which is same as integration a to b v prime t dt, because capital V is a primitive of small v, and then by fundamental theorem, this is vv minus va. So therefore, I know the integration's value is this one and this value is this one. If I add it, then it will be exactly equal to capital FB minus capital A, because capital F of t is nothing but capital UT plus IVT. So therefore, if the primitive of small u and small v exists, then primitive of small f exists, and by fundamental theorem, I have the value of integrations a to b f t dt, which is nothing but capital FB minus capital FA, where capital F is the primitive of small f. Okay, so that is like the same way I can parallelly generalize in the context of complex valued functions of real variable. Now, couple of properties you can have it. I am not going to prove it, so it is very straightforward, like the case in the real valued functions of real variable you will have it. So if I have two complex numbers, if I have two functions, see look, I am saying that not continuous on the full, but if I have a piecewise continuous functions. Now piecewise continuous means what? So that means it is not continuous on the full domain, but it is continuous except finitely many. Therefore, so suppose for example I have A to B, right? So that means it is continuous everywhere, but except say finitely many points. So that means it is not continuous. That means it is continuous in this piece, in this piece, in this piece, in this piece, in this piece. So that is called piecewise continuous. No, so the point is that even if I have a piecewise continuous functions, suppose I do not have continuity on the full domain, but I will have continuity almost all except finitely many discrete points, then also I can say that my function is, then I'll say that my function is piecewise continuous, and also the Riemann integration exists. Okay, so that is the theory of Riemann integrations. You can, if you recall it, even if my function is piecewise continuous, then the Riemann integrations of my functions exist. So that means I do not need the continuity on the full domain, but even if I take finitely many points from the domain, and if I have continuity of my functions, that means my function is continuous piecewise, not on the full domain, then I can still, I can say that my function is Riemann integration or Riemann integrable. So that's exactly things. So alpha and beta two complex number, f and g are two continuous functions or piecewise continuous functions, complex valued functions. Then this linearity property satisfies. That means integrations a to b alpha ft plus beta gt alpha will come out. So therefore integrations a to b ft dt plus beta times integrations a to b gt dt. Number 2, if ft is continuous or piecewise continuous complex valued functions on the interval a to c, and if I take some point b in between a to c, then integrations a to c ft dt I can break up into two parts, integrations a to b plus integrations b to c. So this kind of properties you know for real valued functions of real variable. Same thing also true in case of complex valued functions of real variable, because I am just writing my complex valued functions into two parts, and each part is real valued functions of real variable. That is why all properties should be parallelly you can extend in this context. Number 3, if ft is continuous or piecewise continuous complex valued functions, then in the real case also you have seen, if I change the variable a to b to a, then there will be a sign changes will be there, -1, and this is kind of properties also true, because since I am dealing with complex valued functions, so therefore integrations a to b ft dt will be a complex number, right? So the thing is that can I estimate my this number? So it says that if I estimate my integrations a to b ft dt absolute, this is dominated by, you can push your modulus inside the integrand. That means it is dominated by a to b absolute of ft dt. Maybe that one I will talk about. That also you can prove it using the theory of whatever theory or properties I have discussed for this integrations of complex valued functions. Maybe in my next slides I will talk about that. So that means I can estimate my integrations a to b ft dt. If I take the modulus, it is dominated by the integrations a to b modulus of ft dt. That means I can push my modulus inside the integrand, but provided there should be inequality. That means it is dominated by. Okay, so that is important. Like for example, real and imaginary part. So they are what? Therefore, real part of integrations a to b, I can push the real part inside the integrand, but there is equality. Imaginary part of integrations is the equality. However, if I take the modulus, it should be lesser equality. It is not the equality. If I take the absolute of the integrations a to b, which is dominated by a to b modulus of ft dt, that means I can push the modulus inside the integrands, but there will be a what is called inequality sign. Okay. So maybe I'll just prove this one, and that is also easy. So proof of 3. Now suppose your my functions f is integrable. So therefore this integration will exist. It will give you a complex number. Let it be r e to the I theta. One fixed complex number it will give. Suppose I am considering the what is called polar representation r e to the I theta. What is r? R is the modulus of the complex number. That means integrations a to b ft dt. Okay. Now look, so what is r? So from this inequality, you just take e to the I theta in this side. So what will happen? This should be e to the power minus I theta times integrations a to b ft dt. Now what is e to the minus I theta? That is a constant, right? So because because this is a fixed complex number, integrations a to b ft dt. So therefore this is a fixed complex number, where r is the modulus and theta is the argument. So therefore this is a fixed complex number. So therefore if I hit this complex number, I can push this constant inside the integrand. So therefore this is same as integrations a to b e to the minus I theta ft dt, right? Now this is very nice. So I have r is exactly equal to this integrand, right? That is perfectly all right. Then what will happen? So now look, so yeah, I have a r. What is that? This is a to b e to the power minus I theta ft dt, right? So therefore I have a new integrand, right? So I have an integrand, suppose let it be gt. So gt is nothing but e to the power minus I t ft dt, right? Now if I have this equality, now if I take the real part on the both sides, then what will happen? Real part of r, which is same as real part of integrations a to b e to the power minus I theta ft dt, right? But what is real part of r? R is positive, no? This is a positive real number. So therefore this is same as r is equal to real part of integrations a to b e to the power minus I theta ft dt, and that exactly I have written. So this r, which is same as real part of this, and this is my integrand, right? But now when I was talking about, or when I was defining the integrations of complex valued functions, then I said that you can push the real part inside the integrand. So therefore this is same as real part of this object, okay, e to the minus I theta ft dt. So what it turns out is that if I write my integrations a to b ft dt of the form r e to the I theta, because it's a fixed complex number, then r is exactly equal to integrations a to b real part of e to the minus I theta ft dt, okay? That's what I have it. But what is r? R is nothing but this absolute. So come back here. So therefore absolute of a to b ft dt, which is same as r, which is same as this, I already proved. Now this is very nice. Look, what is that? Now I have, so look, so I have a integrations a to b real part of this. Now real part of this means what? That means it is integrand is now real valued functions, because this is a complex number, but I am talking about real part of this complex number. That means this integrand is real valued. So therefore I have this function. So let it be say gt, which is real part of e to the minus I theta ft, right? So this is real valued functions, but I know real part of any complex number which is always dominated by the modulus of the complex number. So therefore I can say that this is always dominated by modulus of e to the minus I theta ft dt, okay? So what I have used? So real part of z is always dominated by mod z. So that inequality I have used. So I have this one, right? Now this is a real valued function, this is also a mod is a real valued functions, and in real analysis I know if f is less or equal to g, then integrations a to b is less or equal to integrations a to bg. So same thing. So therefore real part of this object is dominated by modulus of the complex number. So that means this is less or equal to this. Then by theory of real analysis, integrations a to b, real part of e to the minus I theta ft dt, which is dominated by absolute of e to the minus I theta ft dt. But what is the absolute of this one? Absolute of e to the minus I theta is 1. So therefore what will remain is that integrations a to b ft dt. So therefore look at the left hand side. So if I take the absolute of my integrand a to b ft dt, then this is dominated by integrations a to b modulus of ft dt. That means I can push my modulus of the integrations inside the integrations, but there should be a inequality, okay? So this is like a nice trick. So that means this is the trick actually, okay? Fine. Okay, so this is like as I said, this is just simple extensions of your Riemann integrations that you are familiar with for real valued functions of real variable to the complex valued functions of real variable. Now I am going to define what is called, if I have a complex valued functions of complex variable, so suppose it is defined on D, and suppose inside my domain there is a contour, okay, then what is the meaning of the integrations of f over that contour, okay? So that's what, so let f from D subset of C to C, is it possible to define Riemann integrations f over a suitable class of curves, namely contours or say piecewise smooth curves? I'll explain what do I mean by contours or piecewise smooth curves. So that is, so same concept, that's the same thing, that is the line integral, or I'll say that if I define complex valued functions of complex variable, integrations of that complex valued functions over some contour, then this kind of integral is called contour integral of f, can be defined over a suitable class of curves. But before that, to introduce line integral, that is called contour integration or line integrations, okay, because I'm talking about the integrations of my function shape over a contour, okay, so that is called contour integration or line integral. You see that with the help of theory of Riemann integrations that you are familiar with in case of real analysis, using that concept you will be able to define that one. Okay, maybe I need some little extra notation, that is called what is called Riemann Stieltjes integral. That means if you comfortable with Riemann integrations, then there is a corresponding little kind of extension of this Riemann integral, that is called Riemann Stieltjes integral. Okay, so still Riemann Stieltjes means I have a functions a, but this time I am integrating my functions with respect to functions of bounded variations. There also you can make sense of this kind of integral, that is called Riemann Stieltjes integral. And in particular, if I take the functions of bounded variation is f of x, say g of x is equal to x, it turns out that it becomes what is called Riemann integrations. So I need that notion, just the definitions, nothing else. Okay, so once I have the notions of what is called Riemann Stieltjes integration, then using that concept of Riemann Stieltjes integration, you can talk about what is called line integral or contour integral. But since I am talking about contour or piecewise smooth curves, so I need to start with, say, what do I mean by curve, what do I mean by contour. So let me start with the concept of curves. Okay, so what is the definition of curve? Curve is that a curve gamma, so I think this is quite common, I hope, again I just recall it. So a curve gamma is a continuous complex valued functions defined over T or in some interval. So that means it says that, okay, a curve gamma is a complex valued functions, of course, it is continuous, but it is defined on what is called real variable. Either it is defined on the full real line or it is defined on the part of the real line, say some closed interval a to b. Okay, so a curve gamma is a continuous complex valued functions gamma defined for T in an interval of the real line, either on the full real line or in the part of the real line. That is, a curve is a continuous function as gamma. You see I have written, it is defined on I, which is subset of R, but taking values in C, where I is an interval or it can be the whole of R. So that is the meaning of my curve. Now if I have a curve, then of course you can, you see the couple of examples I have given. So therefore I can draw my curve. If I have a complex valued functions of some real variable, I can draw my curve in the complex plane. So if I have a complex plane, this is my complex plane, then you can see, for example, look at this one. Number one, it says that this is a curve. Okay, what is that? Because I am defining gamma. Okay, and what is that map? It's a map from closed interval 0 to 2 pi to C, because T runs from 0 to 2 pi and it is taking values e to the it. That means it is taking values in the complex number. Now what is e to the it? This is cosine t plus I sine t, right? This is the meaning. It is a curve. And why it is a curve? Because your gamma t, which is cosine t plus I sine t or e to the it, but you know I already discussed that t goes to e to the it, so this is a continuous function. Why it is a continuous function? Because this is a continuous function, this is a continuous function. Since the component functions are continuous functions, so therefore my functions gamma is continuous function. So therefore this is a continuous function, it is a map from closed interval 0 to 2 pi to C. So therefore by definitions of curves it says that it is a curve. Now you can draw a picture here, because if I have a complex plane, it is taking, because from t from 0 to 2 pi it is taking values in C, and what sort of values? Cosine t plus I sine t. Now what is the absolute of gamma of t? What is that? This is e to the power it, and what is that? This is cosine t plus I sine t, right? And what is that? This is that absolute of the complex number, square root of cos square t plus I sine plus sine square t, and what is that? This is 1. So therefore if I draw a picture, it will give you a circle in the complex plane with center 0 and radius 1, and that is the example. Okay, this is a curve. This is also a curve. It's a straight line joining two distinct points z1, z2 and given by, okay, suppose if I have a complex plane, suppose this is my z1, this is my z2. So the line segment joining z1 and z2, so what is the equation of a line joining 2 points x and y in the real case? You know, it's t times x plus 1 minus 2 times y, right? Same thing, t runs from 0 to 1. Now if I have two complex numbers z1 and z2 and I want to give equations, the line segment joining z1 and z2, same thing. So this is nothing but t times z2 plus 1 minus t times z1, t from 0 to 1. That means if t is equal to 0, it will start from z1, and if t is equal to 1, it will end up with z2. So therefore it starts from z1, it's z2. And what kind of functions? This is gamma t is equal to t z2 plus 1 minus t times z1. This is also continuous functions, because why? Either you can say that as a function of t it is very nice polynomial in t, this is a continuous function, or maybe you can say that I can break up into two parts and each component are continuous function. That's also a way you can think, because z1 and z2 are fixed. Okay, so therefore you can say that this is also continuous functions. So therefore gamma of t, which is t times z2 plus 1 minus t times z1, so this is also a continuous functions. This is a curve by definitions of curve. And what is the curve, how it looks like in the complex plane? It is the line segment joining z1 to z2. Okay, so continuity I am not checking it. Continuity is very straightforward, because the map t goes to gamma of t, which is t times z2 plus 1 minus t times z1. It's very straightforward continuous. But you can say that, okay, there are many ways you can check it. Okay, so for example, how it looks like. So this is t z2 plus 1 minus t times z1. You can say that. So this should be t times z2 minus z1 plus z1. So this is a fixed complex number, and what kind of map? This is gamma of t. So that means this is fixed, z1 and z2 are two fixed complex numbers. So therefore this is a fixed complex number, this is a fixed complex number. So therefore what kind of map you will have? You will have gamma of t is some constant at plus b, and this is a polynomial functions of t, so this is a continuous functions. So therefore this is a continuous functions, and it will be a curve, and how it looks like in the complex plane, it is a line segment joining z1 ending at z2. Number three again, from the clear. So what is the real part? So you can think about this is gamma of t, you can say that this is t comma t square, right? So what is the real part? Real part ut is equal to t, and imaginary part vt is equal to t square. So you can say that ut is equal to t and vt is equal to t square. Now u and v both are continuous functions because it is a polynomial in t. Since u and v are continuous functions, so therefore my gamma is continuous functions, right? So therefore it is a curve. But here t runs over r. Now if I draw a picture on the complex plane, it will be a what is called parabola. So it's a parabola. So you can think about in like what is called in R2 case. Suppose this is my x and this is my y. And what this equation will give? This equation will give is exactly equal to y is equal to x square, and y is equal to x square is nothing but the parabola in R2 case. So same thing. And second one is the what is called line segment joining z1 to z2. So these are the very simple examples of curves. And this is sometimes this gamma is called the parameterizations of this curve. Okay, so if I have a curve in the complex plane, then gamma is called the parameterizations. Okay, so these are very simple examples of curves. Okay, so then maybe I'll talk about, so curve I have defined. So once I have a definitions of curve, so suppose I have a complex valued functions of real variable, either it should be whole real line or part of the real line. If my function's gamma is continuous, then I'll say that it is a curve. Very simple examples I have discussed. For examples, circle, then you have a straight line, then you have a parabola, then you have ellipse, everything, all are very nice. Okay, so these are the examples of curves. And then once I have the notions of curves, then I'll talk about what is the definition of simple curve, then simple closed curve. So those definitions will come in my next lecture. So I think I should stop for the timing, okay, for this notions of curves. In my next lecture, I'll start with the notions of what is called simple curve, simple closed curve, then you'll have a Jordan curve, then there is a theorem called Jordan curve theorem, and then I'll talk about contour. Okay, so once I have the notions of contour, then I'll move my discussion what is called contour integrations or line integral. I think I should stop here. In my next lecture, I'll start with the definitions of what is called simple curve. Okay, so I think I should stop here. Thank you.